equation 4, if you want to find d del by dt, you can take square root. So d del by dt will be equal to root of 2 by m into integral del naught to del pa d del. So let that be equation 4a. Now we will move on to the next equation, where d del by dt can be written as d del by dt equals d theta e by dt minus omega s. From here we have already seen that del equals theta e minus omega s into t. So we differentiate that equation. D del by dt equals d theta e by dt minus omega s. Now let this be equation 4b. Now from equation 4b, it means that the relative speed of the machine with respect to the synchronously revolving reference frame must become 0 for stability, because d del by dt equals 0 is the condition for stability. So the relative speed of the machine with respect to the synchronously revolving frame, reference frame, must become 0 here. This becomes 0 for at some time after the disturbance, because once the initiating disturbance has occurred, it will have some oscillations, and after some time it will settle down to a new point, new operating point, steady state operating point with a new power angle value. Now from equation 4a here, from equation 4a we can write that integral del naught to del pa d del equals 0 for stability condition. For stability condition, d del by dt equals 0, which implies this one, right? Now let it be equation 5. Now let's see the plot of power and power angle, active power and power angle. I'll draw it here. Let it be like this. So now initially, if the machine is operating at angle del naught, some steady state operating point. Okay, so this is the steady state operating point at which the system is operating at power angle del naught, where as this is a steady state operating point, we have P E naught equals P M naught. Mechanical power equals electrical power. It's in equilibrium. Now, if from the equilibrium point corresponding to del naught, P E naught and P M naught, if there is a sudden increase in input power in the sense input mechanical power to the point Pm, that is initially it is Pm naught, now it is moved to Pm. Okay, moved to Pm. So corresponding to Pm, here another value is there. We don't know, some value, let it be del 1. Okay, now this region, what is the importance of this region? This one, this region. This is the accelerating area, because at present Pm naught has increased to Pm, but Pe is still Pe naught, right? So there is accelerating power, which is Pm minus Pe naught equals Pa, accelerating power. So this is the accelerating region. So if we take this area from here, if we take this particular area, let it be A1, let this be A1. This area is known as accelerating area. Accelerating area A1. Okay, or as accelerating power is positive at this region, the excess energy stored in the rotor during initial acceleration is represented by the area A1. Okay, the excess energy stored in the rotor or the energy gained by the rotor during initial acceleration is represented by the area A1. But now we see that del naught has increased to del 1. Now if it increases to del 1, what happens is PE also increases. PE started with PE naught, the equilibrium point PE naught. Now it is increasing to PE with increase in del. Right. Now what happens? If we take this integral del naught to del 1, that is corresponding to the accelerating area, the power angle variations corresponding to the accelerating area, and if you integrate the accelerating power, what will you get? You will get the area A1, right? Let it be, I'm going to represent it as A, then B, right, B and D. So let it be area ABD. Okay, or okay, it's small letter ABD. ABD. Now let it be equation 6. Equation 6. Okay. Now this can be written as integral del naught to del 1 PM minus, what is PE? PE is P max sine del, right? P max sine del, d del, right? Which is equal to again area A1, right? Equation 6 can be written as this. Now when del increases, PE also increases, and at del equals del 1, PE matches PM or PE equals PM. So we know that that should be the new operating point, but the path to the new operating point is not just this. It will not directly jump from here to the new operating point, which is a steady state operating point. It will have some oscillations. Because of inertia, it may not be able to stop at this point. So it will exceed this point and it will go to some point here. Right. So what is that point? Let us see. Let us represent that point as C. Okay. Now corresponding to that C, we have a power angle value here, which is del 2. Okay. Now this is the corresponding P value, PE value or PE value, because PM is constant here, right? PM is the input has increased from PM naught to PM. So PE is going this side. When in this region, we know that PE is greater than PM, right? That means it corresponds to negative PA, negative accelerating power, which is decelerating power. Now, because of this decelerating power, what happens is we get another area here, which is area A2, which is known as the decelerating area. So because of this deceleration, what happens? It stops here and it comes back. When it comes back after this point, again it goes to this side. But every time the oscillation amplitude decreases if there is a damping power in the system. So finally it happens to be at this point where the new PM equals PE, some PE, which is del 1, which is corresponding to del 1. Okay, now let us see how it can be represented mathematically. So because of inertia of the rotor, del increases beyond the point del 1, right? Beyond the point del 1 at a speed above synchronous speed because it is accelerating, right? Then correspondingly electrical power also increases beyond the new PM, which is this one, beyond the new PM, which implies the rotor decelerates until del equals del 2 here, until del equals del 2. From this point it comes back. Now according to equation 5, this is equation 5, right? According to equation 5, the rotor must swing past point B until an equal amount is given by the rotating mass. That means whatever is gained during this region should the rotor should give out that particular energy in this region. So if A1 equals A2, then it will come back. At that point it will come back, right? The energy given up by the rotor as it decelerates back to the synchronous speed, that should be found out again, because the energy that is gained by the rotor is found out by equation 6, the accelerating area A1. Now corresponding to decelerating area A2, we have to find the energy, which is integral del 1 to del 2. Now earlier it was del 0 to del 1, right, for acceleration. Now it is del 1 to del 2. From del 1 to del 2, PE is more than PM. So PE minus PM is the decelerating power. D del equals area A2. Right. Let it be equation 7. Now, area 1 should be equal to area 2. Area A1 should be equal to area A2. Right. So this back and forth swinging at natural frequency settles out at point B, the new steady state operating point. This is point B. This one. This is point B, which is the new steady state operating point if there is damping in the system. Otherwise it will go unstable. Okay, that is all around a different case. We'll discuss about that. So now if area A1 equals area A2, we will equate those two equations. Del 0 to del 1 PM minus P max sine del d del equals integral del 1 to del 2 P max sine del minus PM. This is PE. Okay, this is PE. D del, which is equation 8. Okay, which is equation 8. Now let's see. Let me change the color. 1 minute. Okay. Okay. Now this equals PM into del 1 minus del 0. I am applying the limits here, plus P max into cos del 1 minus cos del 0 equals PM into del 1 minus del 2, applying the limits in the RHS, plus P max into cos del 1 minus cos del 2. Let it be equation 9. Okay, now we know that PM means new PM. It was earlier PM naught, right? Now it is increased to PM. Now it is equal to P max sine corresponding del is del 1, right? So this can be substituted in equation 9. If this is substituted in equation 9, we get P max into del 1 minus del 0 into sine del 1 plus P max cos del 1 minus cos del 0 equals, this is a LHS, equals P max del 1 minus del 2, this is the RHS, okay, sine del 1 plus P max cos del 1 minus cos del 2. Let it be equation 10. Okay. Now we simplify equation 10, and the last expression, the simplified expression we get is del 2 minus del 0 into sine del 1 plus cos del 2 minus cos del 0 equals 0. This is equation 11. So this is the final expression we are getting, final equation we are getting corresponding to the stability condition area 1 equals area 2. Okay, so using this concept we can find the maximum permissible value of del for which the system will be stable. Okay, so that we'll see using some numerical examples. Thank you.